I'm Christopher Taylor from Tactical Computing Laboratories, and today I'll be doing a presentation on Nim Sandia OpenSHMEM and Nim-HPX. Here is an overview of the presentation. I'll provide an introduction to Tactical Computing Labs, provide a definition of the cloud from an HPC perspective, contrast that with the definition of HPC, explain why HPC developers should seriously consider Nim as a point of integration, provide a value proposition for that integration story, and then we'll get into the Nim Sandia OpenSHMEM and Nim-HPX libraries. Tactical Computing Labs is a research and development firm. We specialize in scientific and numerical computing, machine learning AI, graphs, and digital signal processing applications. We have expertise in RISC-V hardware design and implementation. We successfully completed the RAD-RISC program for NASA that demonstrated RISC-V's readiness for space applications. We created a radiation RISC-V chip that was successfully delivered to customers for their space missions. We believe RISC-V as a free instruction set architecture provides an opportunity for hardware developers and software developers to partner together in a co-design environment to come up with novel implementations of instruction set architectures and other microarchitectures. We have expertise in LLVM compiler development. Everyone in the company has a background in high-performance computing, and we provide commercial support for System Architect and the Structural Simulation Toolkit from Sandia National Labs. The cloud from an HPC perspective is an environment for business and enterprise applications. HPC features exist in the cloud in the form of GPUs and RDMA interconnect. However, these HPC features are deployed and consumed or utilized in a very different way than what you would see in an HPC environment. Commodity Ethernet is used everywhere. And what I mean by that is compute hosts use commodity Ethernet to communicate. Storage hosts use commodity Ethernet to communicate, and it turns out storage and compute are typically shared by the same host. The cloud exists to distribute websites, databases, and other business applications across clusters to achieve a high amount of multi-tenancy. The goal here is to optimize utilization from as few nodes as possible for a variety of applications. Resiliency is a priority, and Hadoop and Spark play a role in this space as the business variation of the single program mini data programming style that HPC folks use. However, Hadoop and Spark abstract SPMD under the MapReduce paradigm. Communication in Hadoop and Spark principally occurs through the distributed file system, the Hadoop file system, or HDFS. This means that a process participating in a Hadoop or Spark job will load data off the distributed file system, perform some computation on that data to create new state, and that new state is immediately written out to the distributed file system. This obviously has some performance issues associated with it, but when you think about resiliency being a priority of a business enterprise environment, this particular model of computing or distributed computing makes sense. Machine learning, AI, and analytics are a pivot by the business and enterprise application community towards high-performance computing. This means that this particular presentation should be prescient to individuals working in that space. HPC is an environment for scientific applications, fluid flow problems, weather prediction and analysis, chemistry problems, physics problems, that type of thing. RDMA interconnect or RDMA network interface devices permeate an HPC environment. Compute and storage are split across two clusters, and all the compute hosts are connected together with RDMA. All the storage hosts are connected together with RDMA, and both clusters are connected together with RDMA. Commodity Ethernet is used specifically for the purposes of DevOps or system administration. The goal of an HPC environment is to optimize utilization of the cluster for a single application. Traditional parallel machines in the 80s and 90s were very cost prohibitive. And in the early 90s, NASA researchers Tom Stirling and his collaborators decided to try building parallel machines from commodity hardware. These were called Beowulf clusters. I want to take a pause for a minute and really kind of highlight something important here. There was an era where parallel machines, or the abstraction or the idea of a parallel machine, was implemented in very custom hardware. The cost, the financial cost of implementing these machines became too prohibitive. What Tom Stirling and his collaborators did was to take a risk on trying to build a parallel machine, to build that abstraction using commodity hardware. And this is very pivotal in terms of HPC history. The Beowulf clusters were programmed primarily through the message passing interface, MPI, and this gave rise to the massively parallel processors, MPPs, the abstraction of that parallel machine being implemented using a cluster. SPMD is a programming computing style that is used in HPC, and communication of state between processes is principally done through the interconnect, the RDMA interconnect. Performance is the priority. Why would HPC developers want to integrate with Nim? HPC is traditionally dominated by C, specifically MPI applications and OpenSHMEM applications. The HPC community, however, is faced with a changing workforce. Java dominated the university scene in the late 90s and early 2000s. Python's become a very dominant language. And finding C developers has become increasingly difficult as more and more C developers are bringing C++ to their applications, which means that C++ has made big moves into the HPC space. Fortran's always been an HPC language, and alongside that, Chapel, Julia, Rust, UPC, UPC++, and Legion all exist specifically for the purposes of opening up access to HPC resources to more people to participate in the community. Nim has a story to make in this space. Talk about value propositions for using Nim in an HPC environment. I'd like to draw your attention to the triangle on the right. This triangle has in the middle of it a solution that's trying to be implemented by HPC developers. At the top of the triangle, we've got the problem. At the bottom left, we have innovation. And on the bottom right, we have existing investments. These three factors on the outside of the triangle work against each other in a lot of ways. And it's the goal of an HPC developer to balance these concerns and these competing factors to come up with that solution in the middle of the triangle. Sometimes developers will spend too much time focused on the problem, where they avoid innovating and they kind of avoid their existing investments. Sometimes developers will spend too much time on innovating at the expense and cost of the problem and an existing investment. And then sometimes developers will spend so much time on their existing investments that they don't innovate and they don't get the problem solved. Nim helps cross-level a lot of these concerns to get to a solution space faster. And what I mean by that is MPI, OpenSHMEM, HPX, UPC, all these technologies have had significant investments from industry and governments around the world since the late 80s. They are foundational HPC technologies, and so there's this question: how can this existing technology stack that has all this investment capital behind it be leveraged for the future? Nim, with its metaprogramming templates, code generation, and form function interfaces, provides a mechanism for integrating those pre-existing solutions into a productivity language. So a Nim user can continue to get the value from these existing investments, particularly when we think about a post-exascale software development environment. Now that clouds and high-performance computers have been differentiated, and a brief explanation for why Nim could add value in the HPC space has been provided, there's going to be a presentation about how Nim and the Sandia OpenSHMEM library has been integrated together. Here's an overview of the presentation. OpenSHMEM will be explained, followed by the implementation details of the Nim-SOS library, be a quick explanation of what is actually provided by the library with a summary and a thank you to those that offered support during the implementation process. OpenSHMEM is a distributed symmetric shared memory library and its origins in Cray research in the 1990s. It provides one-sided communications for SMP-style application development. This means that if you think about how shared memory works or how memory works, a program can read or write to shared memory without any other programs knowing that the read or write event occurred. This is critically important for performance because the CPU doesn't have to context switch between processes or provide any kind of notifications or do any additional work at the operating system level to notify processes that a communication event has occurred and that they should care about it. That being said, it increases the challenge on the software developer side or responsibility to ensure that correct communications are occurring and that program progress is being made and that there aren't any flaws or errors in the application's development. OpenSHMEM creates a partition global address space for parallel applications. Developers have to use the single program many data style to utilize SHMEM. It's a high-performance computing library and a supercomputing technology, and you can read more about it at the link below. If you're interested in providing constructive feedback, there's actually a forum for folks to submit proposals to the OpenSHMEM community for integration into the OpenSHMEM specification. Something I want to kind of highlight here, OpenSHMEM is really a specification, and the Sandia OpenSHMEM library is an implementation of that specification. So you'll see things like TCP/IP being a communication substrate or transport layer for communications in OpenSHMEM. This means that the TCP/IP protocol is still doing handshakes to ensure that data is correctly being passed between processes. However, the semantics of the single-sided communication mechanism are preserved at a high API level. So that's something to think about, right? When you go and you do an implementation of something, the underlying protocols and software and operating system behavior could lead you to a variety of different implementation choices, which, while they preserve what is going on at the API level, they radically provide different performance characterizations and profiles because they inherently have maybe a two-sided communication model associated with them. So when you think about the 90s in a single core CPU environment, people would write codes like the one presented in front of you, a for loop over an array called data. And they're going to take a function, apply it to the data, to a data element to transform it, and then that result is captured back into that element in the array data. Before multi-core, this loop would just run until completion in a single process when it's loaded in memory. Once you think about this loop as the equivalent of a map, right? We're going to take a function, we got some data, and we're going to apply the function to the data, and then we're going to get back an array that represents the results. In the multi-core space, in order to parallelize this, you'd have a parallel for loop over all the data elements, and the code that's within the scope of the for loop would be passed to a bunch of threads that are operating in a pool, and then the parallel for loop would chunk automatically for you subsets of the data array that each thread would have to do work on. In the single core environment of the 90s, in order to get this to work, you would want each process to run on its own independent machine to get parallelism. And you'd end up with code that looks something like this. Assuming an even number of data elements, a power of 2, and assuming a power of 2 number of process IDs, which I've called MPIDs in this example, you'd potentially spin up 4 processes of the same program, and the developer would have to include logic that would partition the data array such that subpartitions are being worked on by each process operating in parallel. So that for loop that we saw in the previous slide is working on a subset of a much bigger set of elements called data. If we were to apply the same techniques that we discussed previously about multi-core, that parallel for loop would run with a thread pool and it would automatically figure out how many elements it needed to work on within that subchunk for each thread running on a different core, right? What SHMEM does is it provides you the mechanism to allocate symmetrically across all those processes a giant array for you to do work on. When a program is compiled to a binary on your hard drive, there's a text segment and a data segment. When that's loaded into memory, the text segment and the data segment get addresses assigned to them in memory, and then a stack and a heap is allocated by the operating system in order to accommodate dynamic memory allocations or static memory allocations. If you go to the man page for end on your Linux system, if you're on a Linux system, or maybe even on your BSD or Mac system, you'll find out that there are 3 pointers that the compiler, the linker, and loader insert into a compiled C program. The first pointer is called eText, there's an eData, and there's an end pointer. The eText pointer identifies the end of the text segment and the beginning of the data segment. Additionally, the eText pointer represents the beginning of the initialized variables in the data segment. The eData pointer represents the end of the initialized variable segment or address range in the data segment. And the end pointer represents the end of the data segment and the beginning of the stack and the heap. This means the address range between eText and eData stores variables that you've initialized in your program. This also means that the addresses in memory from eData to eEnd represent the range of values for variables that have not been initialized by your program. So what SHMEM does when it's initialized is it takes the data segment of your program and registers it with your RDMA network card if you are doing OpenSHMEM programming with RDMA hardware. The RDMA network card has a DMA engine attached to it. This means that your network card can perform address translations and can do reads and writes to and from a process's memory, the data segment. So when OpenSHMEM programs are running on your hardware, on your CPU, when you do a put, which is a write, or you do a get, which is a read, your processor is telling your network card, here's an address for a variable. What I want you to do is perform a read or a write into my memory, and then transfer that information back out across the cluster to a remote host to perform either a read or write operation. So what's happening here is that your CPU is offloading the responsibility for memory I/O operations to your network card. The performance benefit of this should be pretty obvious, but if it's not, what's happening here is that your processor is not having, your program is not having to negotiate with the operating system a data transfer. So your CPU is free to just keep making progress with the program without having to talk to the operating system to get notifications that communication events have occurred, or the operating system itself doesn't have to make copies of the data you want sent and pass it through a chain of memory copies all the way down to the network card for the network card device driver to handle. You're getting direct access to the NIC from your program, and you're telling that NIC to perform I/O operations, and then it just takes care of the rest for you for free. Now, if you think about inter-process communication mechanisms, you've got shared memory, file descriptors, and sockets. Shared memory, of course, is the fastest way to communicate information between processes. It's inherently a single-sided communication mechanism. So if I'm on the same machine, right, and I'm running 2 processes and they're on 2 different cores, those processes communicate with each other over shared memory using the interconnect that's on your processor. If we're talking about file descriptors and sockets, both processes have to request a file descriptor and a socket from the operating system, and then the operating system starts interacting with device drivers. There's all this software that kind of gets in the way. That being said, both those 2 processes are communicating through a file descriptor and a socket over what I assume is going to be shared memory or some other implementation decision that the kernel developer came up with. When we're talking about a network where we've got a variety of machines that are running these processes independently, this creates opportunities for using file descriptors and sockets as mechanisms to interact with a device driver and the hardware, right? And we mentioned previously some of the latencies involved in that because the operating system is engaged. When you think about shared memory and how you would implement that, the InfiniBand or the RDMA hardware NICs create that shared memory experience across a network, right, on different machines so that these processes can act as if they are running on the same machine. And that's sort of the goal of what OpenSHMEM is trying to achieve, is that shared memory mechanism to provide performance in a parallel space. If these processes were threads running on the same device, they could communicate with each other over shared memory. And of course, the only way they would be able to notify each other that a read or a write event occurred is with a mutex, a lock, or like a condition variable, if you're to think about what pthreads provide C developers. How is Nim-SOS implemented? Emphasis was placed up front on providing primary support for basic numeric types, floats, doubles, what Nim calls the sum number types. Specifically, support was provided for scalars and arrays, so I can have a program running that instantiates a scalar, and those scalars are affiliated with each other through the InfiniBand interconnect. So I could read and write to a scalar on a remote host by just passing the address of a value like A, and I could read and write to that remote A. The same stands for the arrays. Implementation required a light use of metaprogramming macros. There's one sort of super macro that makes all of this easier. It's called a symmetric main. And what symmetric main does is it takes a block of code that you've kind of inserted under the macro, and it inserts the OpenSHMEM initialization call at the beginning before all your code gets executed, and then at the very bottom of your code to initialize the runtime system and to deinitialize the runtime system. Additionally, the macro crawls through the code block you've instantiated underneath the pragma and identifies places where you've defined scalars as symmetric and arrays as symmetric. And what it does is inserts what I call shadow variables into the data segment of your program by using in C the static keyword. This ensures that variables you've identified as symmetric when you wrote your code are properly reflected in C as being members of the data segment, which means that the InfiniBand or the RDMA network card can register those variables when SHMEM is initialized and then deinitialize them from the DMA engine on that NIC when SHMEM is deinitialized. This library provides a direct wrapper for the C API in SHMEM, gets, puts, reductions, broadcasts, so collective communications, the implementation of which are either done using binary trees over all the process identifiers or hypercubes over all the process identifiers. Barriers are provided so processes can enter a barrier and then they all block and wait for every process to enter the barrier before they leave the barrier and continue making progress on your program. Quiets are provided. That allows a process running a program to drain its communication queues before making progress on the program. And then there are fence instructions, which operate very much like they do in assembly. Convenience types are provided. I mentioned earlier that we have symmetric scalar support. What a symmetric scalar and a symmetric array are really at the end of the day is a type wrapper over a pointer to that shadow variable that's inserted in the data segment of your code when it's compiled down to C. Nim's typing was really convenient for distinguishing between C pointers from arrays. That was one of the things I really appreciated about Nim and what it adds to sort of the conversation in HPC. Some symmetric types are created for scalars and arrays. So the compiler can now reason about a family of types that are symmetric when you write OpenSHMEM applications in Nim. Iterator support is provided, sync, destroy, copy semantics are implemented, and then support for open arrays is provided. Functions were overloaded to handle scalar to scalar and scalar array and array to array interactions. And I want to thank the folks who worked on the Nim Stood Atomic library. That provided a lot of inspiration on how to implement this API and to provide all these convenient types to handle a variety of different interactions. Here's an example of a Nim OpenSHMEM program. You can see the symmetric main pragmas at the very top, right above that red circle. And in this program, we've got an array of keys with 10 elements. One of the things I want to point out is that the sim-s array is called a symmetric static array. I understand static means something very particular in the Nim jargon. Unfortunately, I couldn't find another way to sort of describe an array that at compile time knows its own size, or the developer knew exactly how many elements to instantiate at runtime. This particular array is different than your typical symmetric array because the symmetric array is, of course, allocated dynamically during the execution of the program. This makes registering the memory with the NIC a little bit harder for OpenSHMEM, so you get a little bit of a performance hit over just statically initializing the array to 10 elements. Below that initialization region, we have the binary search algorithm. You'll note that there's an NPEs function call 5 lines of code down. NPEs is OpenSHMEM providing your program the ability to find out how many processes are currently executing this program in parallel. At the very bottom of this code segment, you'll see that there's a region where we actually have the main section of the program running. There's an errors variable to count the number of times binary search wasn't successful in finding a particular key. You'll see that the keys array is populated using the myPE function call. That's a function provided by SHMEM to tell your program what its process identifier is, what its PE identifier is. Underneath that, we have a barrier, which means all copies of this program running in parallel hit the barrier and they block until all the processes enter the barrier, and then they all leave the barrier. It's a synchronization function. And then we start getting to work. The binary search is executed, errors are accumulated, and the program terminates. So in summary, the Nim Sandia OpenSHMEM wrapper works and is available today. You can find a link to it below on GitHub. Nim is a high-performance computing solution. This means that if you're interested in HPC application development or learning how to write SPMD programs, you can download the Sandia OpenSHMEM library and install it on your system and get to work today using this technology to solve a problem. I want to thank the OpenSHMEM community for putting the specification out, making it publicly available. I want to thank the Sandia National Labs folks for providing their implementation, and of course the Nim community for answering questions that Tactical Computing Labs had along the way to get this implementation completed. This slide demonstrates NimHPX's for each loop support. You'll see we've got a function fn that's been exposed to C using the C decal pragma. That's a requirement to use this functionality. The first invocation of for each uses a par exec, which is a parallel executor. This tells the for each loop to run in parallel. The second argument is a set of values to perform some operation over, and the third argument is the function that's being applied over the data set. Beneath that, the second invocation of for each is done in parallel because par exec is being supplied. Values is being used again as the input set of values to the for loop. And then we've got this third term, which is different than in the previous invocation. And the third term in this case is n, the first n elements that the for each loop needs to occur over. At the end of that function invocation is fn, which is the function that's going to occur inside the scope of the for each loop. Beneath that is the sequential executor example. It's just like the parallel executor example, except seek exec, the sequential executor, is the first input argument to the for each loop. This slide demonstrates the transform reduction, and reduction functionality provided by the library. You'll see at the top we've got two functions, AP and XSFM. Both functions are exposed to C using the C decal pragma. This is a requirement to use this functionality. The first invocation of transform is performed sequentially. It has an input set of arguments, R values, followed by an output set, which is FR values, and then the transform function. All this transform is doing is converting a set of integers into a set of floating point values. Transform reduce is next. It's very similar to transform. You'll note that we've got the executor as the first parameter, a set of input values, and then the third argument is 0.0. This is initialization value for the output of the transform reduction. In this case, we've got FFTRM, which is a floating point value, so it'll be initialized to 0. After that, we have AP, which is the reduction function. We're just going to sum the values after the transform is applied. And then there's XSFM, which is a transform function that casts integers to floats. At the very bottom of the slide, we've got the reduction itself. It's very similar to transform reduction in the transform. We have an executor as the first input parameter. We have a set of input values. We've got the initialization value for the output, which is 0, 0. And then we have the reduction function itself. In this case, it's AP. This concludes the review of the functionality provided by Nim-HPX. Now that we've completed the Nim OpenSHMEM library presentation, you should have an appreciation for what efforts HPC folks put into implementing these types of libraries to perform parallel computations. You should have an understanding of what PGAS means, and you should have an understanding of how SPMD codes are implemented and what types of tricks and techniques are applied to get best performance out of hardware. We're going to pivot now into Nim-HPX. HPX is an implementation of a different model of doing parallel distributed computations. The presentation will introduce the Stellar group. We'll provide a definition for what HPX is. It'll talk a little bit about how Nim-HPX is implemented in software. We'll talk a little bit about what is provided by the library, what's next for the library in terms of features and functionality, give a quick summary of what we've discussed today, and then give thanks to those who provided assistance along the way. Stellar Group is an international research team. They focus on implementations of new parallel computing approaches and techniques. The goal is to get efficient use out of hardware under what they call the Parallel X model. The Parallel X model provides an active global address space, which allows developers to instantiate objects in a global address space in which those objects can move around to different hosts. SHMEM has PEs, which is an identifier to distinguish between a copy of a program running on a system or multiple systems. HPX has a concept called localities. The Parallel X model is the specification or the definition of an asynchronous many-task runtime system. Louisiana State University, Arizona State University, University of Oregon, and the Swiss National Supercomputing Center all participate in this research team, along with open source developers around the world. You can find their source code at the link below, and you can provide constructive feedback or participate in the development through that link too. HPX is a runtime system, so it's a system-level software library. It's a library that provides thread implementations. It provides data structures like distributed vectors or distributed hash tables. It's an asynchronous many-task runtime system. It implements the ISO C++ parallel library that's found in the standard template library, and its implementation is compliant with the specification. It provides for asynchronous function invocations through the use of futures and data flow. Data flow is the ability to recursively execute futures that have been defined ahead of time during compilation. HPX implements a distributed, globally addressable object instantiation mechanism, so you can instantiate objects on different hosts, and you can perform remote method invocations on those objects, along with executing functions on those objects. HPX implements a partitioned standard vector from C++ and a partitioned standard unordered map, which is equivalent to a hash table. In Nim terms, you would get a partitioned sequence and a partitioned table. The thread implementation is in user space, and the thread implementation provides a work stealing priority queue. Communication between machines is through messages, and those messages are coalesced during execution of your code. HPX integrates the Apex auto-tuning library. Auto-tuning is the ability for a piece of software to measure from hardware counters the stress or the strain that is being applied to the hardware in order to make better decisions about how to coalesce messages to get better throughput in communications, or how to better schedule threads or rate limit thread execution to better accommodate the stresses and strains being applied to the hardware. That software is created by Oregon State University. Traveler is a performance visualization library that takes trace data from HPX during execution and provides a Jupyter Notebook interface so you can very quickly visualize and identify where your software is hitting performance bottlenecks. That software is implemented by Arizona State University. In sum, HPX implements the Parallax model. It provides support for SPMD programming, if that's your preference. It also provides support for SIMT programming, so GPUs and FPGA accelerators. This diagram should be credited to the Stellar Group. The diagram on the left is a representation of what an HPX program does during execution. You can see the localities. Those are equivalent to machines that are running a program, and each copy of that program has a numeric value assigned to it from 0 to n-1. At the very bottom of the chart, what you'll see is a thread scheduler. Each compute host has a thread scheduler associated with it. That was that user space software I mentioned earlier. Above that's the active global address space, where object instantiations can be registered for global access and communication support. There's also a parcel port layer that's used to manage communication messages between localities. You'll see that there's a gray box with an arrow pointing to a blue box. Those are situations where an object in memory is invoking an asynchronous operation on another object in memory. So the gray boxes and the blue box represent objects, and the arrows are asynchronous function calls. So you'll see in some cases there's a gray box pointing to a blue box on the same locality, and there are gray boxes that will occasionally point to blue boxes on other localities. Those are all asynchronous functions or RMI messages that are happening across the cluster during your computation. The right-hand side diagram is also from Stellar Group. The top piece of that picture is an HPX application, and at the very bottom is the operating system. And you can see in between those two pieces of software is a performance monitoring capability that's equivalent to Apex. You have a thread scheduler, you have a parcel port transport layer, which is how communication messages are passed around. You have an active global address space, and you have local control objects, which are responsible for managing asynchrony. So spin locks, mutexes, condition variables. All that software lives inside HPX. And you'll note that a lot of that software is pulled out of the operating system layer and right underneath the application layer. So it all executes at the same time with your code. This provides better performance. How is HPX integrated with Nim? You'll need a C++ 17 compiler, HPX. It uses some pieces of Boost, not all of it. HWLock, which is a hardware locality library, it accesses the operating system and tells you information about your system, if you have GPU devices, if you have NUMA domains, how many cores you're running with, that kind of information. PAPI, which gives you access to hardware performance counters on the CPU. And then, of course, Apex, if you're interested in getting an auto-tuning capability integrated with HPX. Nim CPP import library is heavily used in the Nim-HPX library. There's significant use of Nim metaprogramming techniques, what I would call some creative uses of Nim templates and macros, and compile time code generation, not only in the Nim side of the compiler, but also in C++. Asynchronous function support is provided by this library, so support for local and remote execution has been completed. You can invoke a function and have it run locally or have it run remotely. And users can annotate functions with pragmas in order to indicate to the compiler that a particular function needs to be manipulated to operate in an asynchronous fashion. Metaprogramming pragmas that indicate asynchronous functions perform the following operations. The function you've identified gets renamed. It's then wrapped with serialization code in Nim, and that code is then exported to C++. So your function goes from having a list of arguments to just a string. Those C++ functions are then pulled back into Nim and wrapped one more time so that when you pass an argument to Nim, your arguments to your functions get serialized into a string. That string gets passed to C++ function that executes your code by deserializing your code and calling the Nim code underneath. So to some degree, there's a bit of an onion peeling exercise that gets performed by the compiler in order to make all of this work. Data is serialized in between these steps of processing in order to simplify the implementation. because at the end of the day, when you run a function remotely, HPX has to still serialize your data into a string or a byte stream and send that out over the cluster if you provide it with arguments that are locally instantiated in order for them to work on a remote host. Here's an example of some functionality that's provided by the library. You'll see that you can query the runtime system with the find all localities to get a sequence of identifiers that tell you an ID that can be used to query or send messages or send function invocations to remote hosts. So we collect all the identities of all our remote hosts and then cycle through them all and print out the most significant and least significant bits of the GUIDs associated with the localities. You can then query for the total number of localities. This feature returns a future that is a C unsigned integer. You'll have to call .get on that future in order to get the actual value from the future and then cast it as an integer in Nim to get the total number of localities. Here's an example of an asynchronous function being executed on a local host as opposed to a remote host. You'll see the function takes 2 parameters. You'll see that it returns a parameter and that it's been annotated as a plain action. Async gets called, and when async gets called, the function during compile time is sufficiently wrapped. Remember we mentioned the onion layers in order for it to serialize the data and send it out over the network along with the function. You'll see that the second argument's find here, which is the identifier used to tell the software what locality to execute on. So find here means we're going to run this function locally, and 2 parameters are passed at the tail end of this async call. What comes back is a Nim integer value wrapped as a future, and when you call h.get, you'll get the value back when that function's asynchronous execution terminates, and it gets printed as standard out with echo. Here's an example of a function that's being executed across multiple hosts or multiple localities. You'll see we invoke main, and from I to the total number of localities, which have been pre-computed somewhere else in the sample code, an async function that calls hello world is being executed on each locality. In order to save space, the function hello has been removed from this code sample. You get back a future that's void, it has no type, and then you still have to call .get to ensure that that asynchronous function call has been properly terminated by the runtime system. Here's an example of how to instantiate a partition sequence. The first thing you have to do is tell the compiler that you're going to be using partition sequences and that the partition sequence you're trying to exercise has a particular storage type associated with it. This particular call to register partition sequence is generating at compile time C++ code that tells the HPX runtime system to provide support for partition sequences. You'll see that when main is invoked, a partition sequence of integers is instantiated, and that each partition sequence has 10 elements in it. That partition sequence is then registered with the AGAS, or the active global address space, with the .register function. What comes back as a future, you call that future with get to make sure the asynchronous registration process is terminated correctly. And then at the very bottom of the code, what you'll see is that the partition sequence is connected, which means that it's now capable of communicating with other partition sequences in the global address space. That also returns a future, and you have to call .get to ensure that that operation properly terminated. Here's an example on how to create a partition table with HPX, or partition hash table. It follows a very similar process to partition sequence. So we've kind of covered what the library currently supports. Classes and object support is a work in progress. In HPX lingo, these are referred to as HPX components. Users can define a type underneath the component pragma along with all the functions and methods or procedures that need to operate on a particular component. And the compiler will generate all the appropriate wrapper code in order to make it possible or feasible for you to do remote method invocations, remote procedure invocations, or remote function operations on that class that's been registered with the global address space. Nim types, when you perform, ideally when this gets implemented, Nim types will be renamed, exported to C++ and wrapped, and then re-imported back into Nim. All the member variables will be re-imported back into Nim through the CPP import interface. Methods and functions will be renamed, exported to C++, wrapped, and then re-imported to Nim, similar to how asynchronous functions are implemented. And the C++ macros that register the types and functions to the HPX runtime will be automatically generated as part of this process. So the boilerplate code is something you're not responsible for having to manage. Here's what the implementation will look like. You'll have a components pragma. You'll define a type with member variables. You'll define a procedure or a method underneath that component pragma, explaining how a function will interact with that type. And then underneath that section, you'll be able to instantiate that class, register with the runtime system or the active global address space, and then you'll go through the process of being able to invoke procedures on that simple type or that user-defined object in the following manner. Note, this is a work in progress, so things may change over the course of the next couple of months. In summary, HPX works today with Nim. You can get access to code below. New features are on the way. Nim, once again, has been demonstrated as an HPC-ready technology. Learning and working with Nim in this particular project has been very fun because it's provided an opportunity to sort of experiment and play around with some of the FFI techniques and some of the code generation techniques provided by the compiler. Thank you very much for your time. I want to thank the Stellar Group for their support in getting this implementation done, answering questions along the way. I would also like to thank the Nim community for answering questions along the way. Real quickly, I'd like to plug some HPC workshops. There's a workshop coming up on asynchronous many task systems and applications. The deadline for posters and abstracts is passed, but if you want to participate, Zoom access is being provided by the hosts at LSU, and you can find out more information below. Additionally, ACM SIGPlan is hosting a conference, the Programming Language Design Implementation Conference, PLDI. It's an annual venue for people who do work in programming languages and implementations to attend and brief the academic community and industry about what they're up to in terms of their work. You can find out more information below. I really encourage people participating in the Nim community to take a look at what they could do in terms of publications to participate in this forum. Thank you very much to the Nim conference organizers for their time and efforts getting this whole thing lined up. And that's the presentation.